Alrighty. Cool. Can everyone see this? Are we good?
Yes.
Oh, great. It's fine. My camera's frozen again. Wonderful. All right. So this is part 2 of Big O. Yay! I also brought memes.
Nice.
I figured I should up my. So just to run over why we use Big O again, it gives us a way to talk about the efficiency of algorithms, which is their runtime. It allows us to judge what makes an algorithm faster, slower, more or less space efficient than similar algorithms. And we can make better programming decisions based off of the Big O of an algorithm. Yay. Let's see. It does this by allowing us to measure time complexity, which is our runtime, and space complexity. It's also written according to the worst performance and the worst case scenario. Just to go over what we did last time real fast, O of 1 gives us a constant complexity. When the input doesn't matter, it always runs at the same speed. O of n gives us a linear complexity. As the size of input grows, the runtime of an algorithm also grows. We have O log n, that's logarithmic complexity. For each time the input grows, processing time required by the algorithm increases by half of what it previously increased by. And we have quadratic complexity. For each time an input grows, processing time required by the algorithm grows in an exponential fashion. Then we have O of n factorial. It's factorial complexity. Don't use it. I did run into like one thing that I didn't cover last time with it. That's like the traveling salesman problem. So that's something you might want to look into for like interviews and stuff like that. And I made a note of that in the notes also. So as you're preparing for interviews, that might be a problem to cover because you might run into it. We also have best, expected, and worst case scenarios. That's basically just allows us to fit the performance of an algorithm in like an average case against another algorithm. So we can actually compare how two algorithms go against one another in their average outcome. But we do measure Big O assuming the worst case scenario. Then space complexity refers to how much space an algorithm takes up in memory while that algorithm is running. So now let's get into new stuff. First, we've got dropping constants. This is one thing from the GA module that I left out from last time just because it makes a little bit more sense to go over today with what we're doing the rest of the day. Whenever we are basically looking at the processing time of an algorithm, constants don't necessarily matter. Take the two code blocks to the right there. Essentially, like, especially as these two loops would grow, as they have more things that go on inside of them, the fact that the loop exists doesn't really matter. You're still looping over the same data. What really matters is the instructions that are inside of that loop. So that for that reason, we don't really count like, oh, there's two loops over the same over the same set of data there. That part doesn't really matter. It's more, hey, there's loops going through the data. we could, like go and inspect like the um, the base code for each one of these, and how it would be executed by the compiler and all that kind of stuff. But that would really kind of defeat the purpose of what Big O does. It just kind of gives us a broad sense of the performance of an algorithm, and basically determine the major impacts. What matters is that like an O of n algorithm might not necessarily have the same performance as another O in algorithm, but the way that they scale will be the same. And that also applies to other kinds of algorithms, not just like O in algorithms. That's all of our different classes. Any questions from that? And dropping non-dominant terms, or dropping constants, I'm sorry. Cool. Now let's talk about dropping non-dominant terms. So for this, when we calculate Big O, we get rid of everything but the most impactful terms. So I've used this example before from last time. I added a little, just a simple loop at the bottom. So basically the n squared Big O notation takes precedence over the O n, because the n squared has a much greater impact on the performance of this algorithm. So like, for example, just with this loop that we've got here, our nested for loops will have 25 executions with them, while our little loop at the bottom just has 5. So you can see, like, as that array would scale and get larger and larger, like this, the n squared part of this algorithm is going to be huge, while the little n part is going to have almost no impact compared to that. So keep this chart in mind. Basically, as an algorithm gets less performant, that's the one that we care about. So like a n factorial is greater than a power of 2 algorithm, which is greater than a n squared algorithm, greater than n log n. So those would take precedence over something a little bit lower, like a constant algorithm or a log n algorithm. Any questions about that? Cool. So now we're going to talk about adding and multiplying runtimes. So we've got, when we have multi-part algorithms, which are manipulating different sets of data, or even the same data but multiple times, we need to find a way to add and multiply those together, essentially. So when do we do that? Adding runtimes. If your algorithm is in the form of do this, then when you're done, do that, then you add the runtimes. So we've seen this example before also. This is just 2 loops. But with this, we've got two different arrays that we're manipulating. We've got array A and array B. So in this case, the runtime is influenced by the size of both of those. So the Big O notation is array A plus array B. Cool. Also, while we're on this, that like this kind of trips me up a little bit, but like essentially the O of n and all of that, like O n squared, n is just kind of a representation of the data that we're getting. So you typically see like the O of n kind of notation where you're only dealing with one data set. But whenever you start seeing like multiple data sets, you start actually like naming those instead of calling them like ON. And the way that these get their names are a little bit confusing, but it's basically just kind of whatever you decide, as long as you're clear, like, oh, this is dealing with this, or this variable is dealing with this set of data, this other variable is dealing with this other set of data. So whatever kind of makes it clear what you're doing.
Wait, so that one, is ON time plus the other N?
Right, exactly. That's basically what's happening. So like you've got this is essentially ON plus N, which normally you would, once you do that, that would become a constant. Like that would be 2N regularly, correct? And we just learned like a couple of minutes ago, hey, you drop constants because they're not important. But whenever we're dealing with two sets of data, like array A and array B,
because they're different.
Are different. So you have to, so you do distinguish between them, and that's where the curveball kind of lies, because previously, hey, this would just kind of be a thing off to the side that you would just drop. But now it's something, hey, we need to like make sure we're keeping track. Hey, this is array A, this is array B. We're doing something with both of these sets of data.
Okay.
So that's the curveball. Cool. And just kind of to touch on that point again, sorry to keep going back to this, but say we had another for loop here that iterated through array A again. There's just an additional one. So we'd have a total of 3 for loops that execute consecutively. So for loop for array A, another one for array A, and then we've got array B. So then you'd have, before you'd simplify it, you'd add them together. You'd have array A plus array B. That'd become 2 array A plus array B.
So,
which you would drop the 2 because it's a constant.
Right. Okay, that's what I was about to say.
Cool. Okay, now we're going to do multiplying runtimes. If your algorithm is in the form of do this, for each time you do that, then you multiply the runtimes. So this would be, previously we'd see like n squared is what this for loop would be. But for this example, we're iterating through array B for every item in array A. So the runtimes are multiplied together, making it array A, or O of array A times array B. This is where it gets complicated. So previously we'd look at this and be like, hey, this is like an n squared algorithm, or a quadratic algorithm, because you'd have n times n, right?
Mm-hmm.
So that would be, we'd simplify n times n to n squared, which is quadratic. This is still technically a quadratic algorithm, but it has to be written differently because we can't simplify it.
Okay.
Same way that we simplify like an n squared algorithm. Because there's no way to like you can't say array A squared or array B squared because they're both discrete values. Let's see. There's another curveball associated with this.
Okay.
So we don't drop terms from different data sets when we're not aware of the data that they contain.
What?
So say this was just array A we were manipulating and only array A. We would have seen, hey, this is array A squared plus array A. We would know, hey, this last array A part isn't a dominant term. So we would just get rid of it. With this, since we don't know what array B contains, we don't drop it.
Okay.
That's basically what this is saying.
So it's n squared plus n?
Essentially, yeah. That's kind of what this would look like. But we would normally, since n would be a non-dominant term, we would normally drop the n. So it would just be n squared. But since we're dealing with two sets of data and we don't necessarily know how big each data set is in relation to one another, we keep both of them.
So I guess like during an interview, we wouldn't say n because the data is different.
Right. Whenever you're dealing with multiple sets of data, you can't, like, the n part kind of doesn't really describe what's actually happening with this algorithm.
Okay.
You use the same type of math to calculate it.
Mm-hmm.
You're still adding those terms up, but
Right.
like if you start, or you're still multiplying those terms, but if you're actually talking about these different data sets, you have to specify what data set you're talking about.
Right.
So I'd say that was the most complicated part of all this is like, oh, like we're introducing, like we've been talking about n all this time, but I guess kind of what the realization you have to do is like, oh, n is just in place of any data that we're getting. So
Yeah.
now we're specifying, oh, hey, n belongs to this data specifically. So.
Yeah.
Let's see. Kind of went over this already. Runs counter to how we calculate big O when engaging with a single data input. Because we always know the single loop would be non-dominant, then we would drop it.
And it's the same data.
Right. Yep. Here's another meme for you. There's no memes. Okay, so now we can talk about a couple more complexities that you'll see out in the wild now that we know that we can multiply and add our n's together. So first we're going to go over n log n complexity. You could run into this being called like linear arithmetic or quasi-linear. But those aren't like official things. So if someone's like talking, like they don't actually appear in any like research things or anything like that, but like internet terms. So. Let's see. So for each time the input grows, the processing time required by the algorithm grows linearly and logarithmically. So this is the orange line on this graph. You can kind of see that kind of means that it is a combination of, like, you've got the blue line and you've also got like that kind of purplish line also. It's basically those two things smashed together.
Okay.
So this is a really common runtime in a lot of sorting algorithms, like merge sort and tim sort and heap sort. So with this, if one item takes 1 second to process, 100 items will take 300 seconds to process. It's because you're combining both that that log time plus that linear time, or times that linear time, whenever you're doing this. So I don't want to get into a bunch of sorting stuff today. I think Michael's covering merge sort next week, so let's make sure he's still doing that. But you'll see a lot better example of what this looks like whenever he goes over that. This is just an example, though, to tide you over. So basically, we're putting 8 inputs into this function. And then each one of those inputs is being reduced by half for each time it runs. So you have a total of 32 runtimes. Like I said, you'll get a much more concrete example when we actually do sorts next week. So, okay, and this is the last one we're going to cover. This is power of 2 complexity, or 2 to the n power. So basically, for each time the input grows, the processing time required by the algorithm will double. So this is that kind of gray line that's on your screen. This is, except for the n factorial, this is the worst performing algorithm type. So we can see this whenever we do like a Fibonacci sequence, or when we call a function recursively twice within a recursive function.
Mm-hmm.
One item, 1 second to process. 100 items will take many seconds to process.
Not millions.
So here's a code example. So this is creating a Fibonacci sequence. It returns the value of the nth value that we're passing in of the sequence. So what makes this a power of 2 complexity is line 4. That's when we're calling the Fibonacci function twice recursively within the Fibonacci function. So basically, for each process that is being spawned, another 2 processes are being created. And then another 2 processes are being created off of each one of those. And another 2 processes are being created off of each one of those. So you can see how like it would not, like, you have tons of processes running just to calculate a number.
So this is the type of thing that was like making our computers freeze like at the beginning of our cohort, right?
Yeah. So this is the thing that Ben did. That was like, hey, don't put a value of over like 20 in this, or you'll be sitting here for 30 minutes waiting for something to happen. So yeah, that's exactly what this is. All right. Any questions about any of this so far? Because we're basically done. Let's see what we covered today. So we did dropping constants. So we want to determine the major impacts of a runtime of an algorithm. So that's why we drop constants. We drop non-dominant terms. Again, we want to determine what is really impacting the runtime of an algorithm and what is most impactful on it. So that's why we drop non-dominant terms. We add runtimes. Again, that quote from the Cracking the Coding Error Review book is really good. I highly recommend reading through that book, by the way, and reading the Go chapter, because that's what basically all of this is from. And then we also multiply runtimes.
Is that book that good?
Yeah.
Probably should get it.
Yeah. I have a few examples that we run through after this. All the examples are from that. There's also like a ton more examples in that book that go a lot further than like what we're doing here. So like if you're interviewing for some big data company like Google or something like that book has everything that you need in it, I would say. Like it goes way in depth. It explains all of it and like why the runtime is what it is. It goes into a lot of that you just can't find like on the internet, because I Googled and Googled a lot of stuff, and a lot of stuff out there is not useful. I would say. So let's see. Next, we also covered the last two of our complexities. Those are not named right on here. Sorry about that. So we've got n log n complexity. The descriptions aren't on this either. We'll skip this slide. Sorry about that. That was Big O. Big O is the time, language, and metric used to describe the efficiency of algorithms. Here's this chart. This chart is gold. Yay. Okay, let's go through some quick examples. I've just got 5 here. They're all kind of either like basic to moderate. A few of them we've seen throughout this. So take a look at this. What do we think it is? And all these examples, like I said, are lifted from that book, by the way. So
I'm ordering it on Amazon right now.
We do get it for free, I think.
Yeah, I just like to have it in my hands.
I get that 100%.
Is it the O sum plus product? I don't know.
No.
No.
Sorry.
It's like, I don't even know.
Right back. Any guesses? All of these are.
Are those both ON?
Yes. So this is ON. Do you know why?
So it's
basically because the the sum is not really dependent on the product, so the sum will run and then the product will run as well. So they're like 2 of the ON ones. That's how I see it.
Yep, that's exactly it.
wait. So it's just ON, it's not ON plus the other N?
Yep. Well, so it is technically, this would be like ON plus N, which would be O to N. And remember, from today, we drop our constants. So the
So
2
it's-
doesn't matter there. It simplifies to ON.
Oh. Okay.
Because we're iterating through, and it's the same piece of data that we're iterating through.
Right.
So we're taking in the array, and we're iterating through it in our first for loop, and then we're doing the same thing again in the second for loop. Just because we're doing it twice doesn't matter. It's the data we're taking in, and what we're doing with that data once we've got it. That's the piece that matters.
Okay.
Cool. So this is linear complexity, as we just talked about. And we dropped constants, making it O of n. All right, next one.
ON squared.
Yes. Do you know what kind of complexity that is?
Quadratic.
Yes, that's right.
Wow, so smart.
Good job, Crystal. So this is quadratic complexity. The inner loop has n iterations, and it's called n number of times. So our runtime is n times n, or more simply, n squared. Good job, Chris.
Thank you.
Next one.
It's ON times n. Or to the n. I don't know. It's quadratic.
It is quadratic. Good job. So what are you multiplying together there for it to be quadratic?
Both arrays.
Yeah, both arrays and array B.
Yeah. Cool. So this is array times A, or array A times array B. So quadratic complexity. Once again, the arrow loop has of array B iterations. It's called array A number of times. All right.
Oh my god.
And log in. No.
I think it's also quadratic like the last one.
Okay. Why do
My
you
guess
think
is
it's
factorial.
What?
I'm guessing factorial. I'm sorry.
I don't know. Go ahead.
I said, I'm guessing factorial for this one.
Okay. Why do you think it's in log n, Vinny?
I don't know. I just kind of guessed.
Okay. That's cool. Cool. Why do you think it's n squared, Crystal?
Because I think it's the same as the last one because we still have those two different inputs and they're nested. So I think it's array A times array B.
Okay. Cool. Then why did you think it was factorial, Jan?
For me, it's just because you're multiplying. That's kind of like 3 n to the power of 3 because n. That's how I see it.
Okay. You're on a really good track, but so this is O of array A times array B. So because we were looking at something a constant number of times, because our last loop is constant, we drop it. Because say array A was a trillion items and array B was a trillion, suddenly that 100,000 items that we've got in our last iteration, doesn't really matter that much because we've got a trillion items in both our arrays. And that's what we're trying to measure with Big O, is as the size of our inputs grow, array A and array, how does the performance change? So since it's a constant, we drop it. Jan was on a good track though with this, because say we had another for loop inside, then that would be into the power of 3, because you're multiplying your first for loop and your second for loop and your third for loop. So
But that would be with another array, right?
that it could be with another array or with an existing array that would be there. So like say we were doing array B in that last one, then it would be array A times array B squared.
Oh, okay.
Let's see. All right. This is the last question. Which of the following of these are equivalent to O of N?
B. There aren't any letters, but I choose number 2.
Yeah, that's what I would go with.
Are multiple ones, I think, that are equivalent. So
There's multiple?
yes, there's multiple.
Oh,
O-N.
okay.
Then D as well. Because it's just adding N and M, so it's still
Uh-huh.
O of N.
And A too?
I think A might be logarithmic. Or actually, I have no idea.
I think, are we also clarifying that it's would multiple data structures be qualifying?
Yes. So like N plus P would be 2 discrete sets of data along with N plus M. Those would be 2 discrete sets of data that we're receiving.
Okay, so I'm going to choose everything except for C.
Well, I think A
Except for
is
C.
fairly similar to C in a weird way. Because it's, well,
Well, P is just less than N divided by 2. So it's just less of the data structure. It's just the same data but manipulated, right?
Right. So
So-
if E is a non-dominant term because there's less of it, what do we
It's
do with
dropped.
it? Yep.
So I'm going to choose A
That
and
was the answer. The O and P and then the O and M for me.
I didn't catch the first part of what you said, Jan.
I was sorry. I was just piggybacking off of Crystal. That's like the ON one.
Yep.
Okay. My final answer is going to be A and B.
Okay.
Yeah, I'm on that same train too.
Okay. Cool.
Where do we put our votes?
I should have made a poll. I didn't think about it. Oh. Okay. Unless anyone has any objections, is that everyone's final answer?
Mine is an A and then the last one, ON plus OM.
I'm with B and D.
Okay. Cool. Are we ready to see the results?
Wait, Vinny, what are your answers? Alana,
I think it's B and D.
B and D.
Yeah.
All right. Let's see the answers.
Okay.
So, kind of already gave away one. If P is less than half of it, it's not significant enough to include, so it can be simplified. O2N, we can drop the constant of 2. That leaves ON. And then we've got N plus log of N. Log of N is a non-dominant term, so it can be dropped.
Oh.
So that leaves us with ON. And then our last one, we've got N plus M. Without knowing anything about either of them, we're unable to simplify it any further. So A, B, and C can all be simplified. The last one can't.
Oh.
Yeah, good question.
It's from
We're all wrong.
it's great. Like it's wonderful. So remember, like we've got, I can't see my mouse on my actual screen, so I have to look at this screen. Okay, so this login is a non-dominant term compared to O of N. So as we go around this chart, these become more dominant up here than the ones down here. So if you ever see anything that is on like this side of this chart over here, then you can know, hey, this is a dominant term over anything over on this side of the chart.
So the green means non-dominant and the red is dominant.
Yep.
And the yellow in the middle is both.
I was thinking like the N plus log N was like equal to N log N, so that's kind of why I thought that. But
That would be if it was multiplying, then yeah. But not in this case.
yeah.
So yeah, like basically as whenever they would reach, so think if this chart was bigger, I guess. Whenever they would reach the top of the chart, then that's what the more dominant term would be. The faster it's going to reach the top of the chart, the more dominant it is.
Mhm.
So looking at this chart, does it like the O log N trumps O1 and then ON trumps O log N? Is that fair to say that?
Definitely. Yep. That's exactly right. Cool. That is all I have. Does anyone have any further questions?
No.
I have a question about this book. Is it all in Java?
So it's I think it's either Java or C or C++, one of those three. I'm not entirely sure. The examples that I've seen in it so far are pretty, like all of these examples in here are basically have just been translated from what they've got. And it's really easy, like to kind of look at it and just be like, oh, this is like they're declaring an array here. And oh, they're finding the length of an array here. Like a lot of the languages basically, so it's not too hard to determine, oh, this is what this is doing.
Sure.
So,
You said you could get it for free?
yeah, I think Alana mentioned that it was free in one of the emails we got last week.
Oh,
I think.
Yeah, I just found it. It was one I think Alex sent out on 420.
I was just curious because there's a bunch of people in the comments bashing it because they're saying it's useless unless you want to learn Java.
Yeah, I wouldn't say it's useless, like, because you can see, at least for this part, at the very least, like, you can see the structure of a for loop. Like, you can see the structure of a for loop in almost any language because it's a for loop.
Mhm. Yeah.
They're structured the
I'm
exact
just
same
thinking,
way.
like, for like the harder questions, like it might be harder to translate.
Yeah, possibly. Yeah. And I think I found a couple of sites online that have kind of translated some of this type of stuff.
Mhm.
And so it might be similar for the rest of it. I really don't know. Cool. All right. Don't have anything else?
No, just want to say thanks, David and everybody. You guys are like amazing, and have a great weekend, everybody.
Yeah.
Yeah, you too.
All right.
We're not meeting on the weekend, are we? Or are
No.
we?
I mean, we can. This room will be here. Any other, if you want to meet, I'm not gonna stop you. But
No, I think I'm gonna go. I'm gonna go boating, so I'll be here.
Enjoy
Yeah.
your week.
Enough
Yeah.
with 5 days a week code challenges.
Yeah.
it's time for a break.
Yeah, exactly. That's where I was going. We need to have a